Students, this is a continuous class. In the last class we were discussing about the reactions of haloalkanes, and we have discussed the substitution reactions of haloalkane. Today in continuation of the previous class we are going to discuss substitution reactions of Rx, let us say alkyl halide. Here we discuss substitution of hydroxyl group, or you can say formation of alcohol. Here, when alkyl halide is treated with aqueous KOH, an alcohol is formed. The halogen atom is replaced by the OH group. That is Rx plus potassium hydroxide aqueous. The product will be ROH plus KX. So this is your alcohol. For example, we can say CH3Br plus potassium hydroxide aqueous, we get CH3OH plus potassium bromide. So methyl bromide gives you methanol or methyl alcohol. The students must remember, in the previous class we have discussed when alkyl halide treated with aqueous KOH, we are getting alcohol. But if alkyl halide treated with alcoholic KOH, you will get alkene. Elimination will be there, but here substitution will be there. Just for the difference. Alkyl halide, on treatment of alcoholic KOH, we are getting alcohol, but same alkyl halide having more than 2 carbon atom, when treated with aqueous alcoholic KOH, we get alkene. Elimination occurs. Now, second substitution reaction is substitution of alkoxide, or in other words you can say formation of ether. Alkoxides are derivative of alcohol. When alcohol is treated with metallic sodium, we get sodium alkoxide, ROH plus metallic sodium, we get RONA. This is your sodium alkoxide. So when an alkyl halide treated with sodium alkoxide, an ether is formed. That is Rx plus RONA gives you ROR plus NaX. So this is our ether. Here the ether may be of similar alkyl group or dissimilar alkyl group. If you want to get to dissimilar alkyl group, then you can add Rx plus RONA. You will get ROR plus NaX. So here you are getting ether of different alkyl groups, or you can say unsymmetrical or dissimilar ether, but this is similar ether where both the alkyl groups are same. So this method helps us for preparation of alkyl ether of different alkyl groups. For example, you can say if you have CH3Br plus C2H5ONA, the product form will be CH3OC2H5 plus NaBr. Now, this is our ethyl methyl ether, ethyl methyl ether. If you want to get dimethyl ether or diethyl ether, you take ethyl bromide and ethyl sodium ethoxide, then you are getting ether. This is sodium ethoxide. So this reaction is now substituting halogen atom by OC2H5 or OR. This reaction is called Williamson synthesis. This reaction is called Williamson's synthesis. Williamson synthesis helps us preparing ether of similar type or dissimilar type. Now, let us come to, these are all substitution reactions. As I told you in previous class, that alkyl halide has a number of reactions. Almost all type of organic compounds can be prepared from alkyl halide. Now, let us come to reaction with metals. Reaction with metals. Reaction with metals. Alkyl halide reacts with a number of metals to give you different types of products. First of all, reaction with sodium. Reaction with sodium. When alkyl halide treated with metallic sodium in presence of dry ether, 2 molecules of alkyl halide condense to give a large alkane, to give a bigger alkane, that is Rx plus Na. Here 2 molecules of this will react in presence of dry ether. The product form will be RR plus NaX, 2NaX, this is 2. So this is your alkane, higher alkane. If you want to prepare higher alkane, then you have to proceed by this method. That is, you can write this in this way, X plus 2Na plus XR. To remember this, we can write it in this way, RR plus 2NaX. So, when alkyl halide treated with metallic sodium in presence of dry ether, we get higher alkane. For example, when methyl bromide is treated with metallic sodium, 2 molecules of this, 2 molecules of sodium, it gives you ether, it gives you CH3 plus 2NaBr. This is ethane. You have started with methyl, you are getting ethane. If you start with ethyl, you will get butane. So in this way, you will start with C2H5 Br plus sodium. 2 molecules of this will condense to give you, in presence of ether, dry ether, it gives you CH3, CH2, CH2, CH3 plus 2NaBr. Now, you see, the alkane is always higher, it is double the number of carbon atom present in the alkyl halide. You are getting higher. This is butane, N-butane. This is ethyl bromide. You mark the difference here. The number of carbon atom present in the final product is twice the number of carbon atom present in the alkyl group, alkyl halide. So this method helps us in preparing higher alkanes. And this reaction is known as Urge reaction. It is called Urge reaction. This reaction is called Urge reaction. Urge reaction helps us preparation of higher alkane from lower alkyl halide. So when metallic sodium reacts with alkyl halide in presence of diether, we get alkanes, higher alkanes. And you must remember, this alkane will always have even number of carbon atom. Odd number of alkane with odd number of carbon atom cannot be prepared by this method. For example, if you want to get propane, if you want to pentane, you cannot use this method. Second reaction is reaction with metallic magnesium. Second one is reaction with magnesium. When alkyl halide reacts with magnesium, in presence of dry ether, we get Grignard reagents. That is RMgX. That is Rx plus magnesium in presence of ether, dry ether. We get RMgX. This is called alkyl magnesium halide. Otherwise, this is called Grignard reagent. Grignard's reagent has a lot of application which you will read in subsequent classes. This is called Grignard reagent. So Grignard is alkyl magnesium halide. For example, if you treat with methyl bromide plus magnesium in presence of dry ether, the product form will be CH3 magnesium bromide. So methyl magnesium bromide, it's a Grignard. It is a Grignard reagent, and the reaction, name of this compound is methyl magnesium bromide. This is also a Grignard reagent, which is otherwise called organometallic compounds. So these are also otherwise called organometallic compounds. Organometallic compounds are known as Grignard reagent, and when alkyl halide treated with magnesium, you are getting ether. Another reaction is that of reaction with lead. Reaction with lead. When Grignard reagent is treated with lead, when alkyl halide is treated with lead, we get a compound called tetraethyl or tetraalkyl lead. So reaction and when you can say when Rx reacts with sodium lead alloy, tetraalkyl lead is formed. For example, you can say when methyl bromide is treated with sodium and lead, you can say PbNa. 4-PbNa. This will give you a compound is called when ethyl bromide is treated with an alloy of sodium and lead, we get C2H5 Pb, C2H5, this is C2H5 plus 4NaBr. So this one is called tetraethyl lead, which is otherwise called TEL, T-E-L. Tetraethyl lead is a synthetic compound which is used as an anti-knock material in your petroleum vehicles. Another reaction of this alkyl halide is Friedel-Crafts reaction. Friedel-Crafts reaction. Friedel-Crafts reaction, when alkyl halide is treated with benzene in presence of anhydrous aluminum chloride, alkyl benzene is formed. That reaction is called Friedel-Crafts reaction. Friedel-Crafts alkylation, for example, you can say when benzene is treated with RX in presence of anhydrous aluminum X3 or anhydrous ferric chloride, X3, FeX3, the product form will be R plus HX. So this is alkyl benzene. For example, benzene when treated with methyl bromide or methyl chloride, whatever you call it, methyl chloride in presence of anhydrous aluminum chloride or anhydrous ferric chloride, whatever may be this anhydrous aluminum chloride, the product form will be CH3 plus HCl. Here methyl group is substituting hydrogen of benzene. This is benzene, this is methyl benzene or it is called toluene. Methyl benzene or toluene. In this way, you are substituting an alkyl group on benzene, and you can substitute any alkyl group depending on the nature of the alkyl halide. If you want to substitute an ethyl group, then you have to take ethyl chloride. If you want to take propyl group, you have to take propyl, in this way. So that method substitute an alkyl group on benzene, and this reaction is called Friedel-Crafts reaction, and this also comes under the alkyl halide. So these are the compounds of reactions of alkyl halide. Now let us come to another topic of this chapter, is that of haloalkane, so haloarine. Now we will start another topic, is that of haloarine. Haloarine, or you can say aryl halide. Aryl halide is nothing but the substitution of halogen on benzene ring or aryl group. When you can say when a hydrogen atom of benzene ring is substituted by a halogen atom, the product is called aryl halide. That is, if you take C6H6 minus hydrogen plus X, you get C6H5X. This is your aryl halide or haloarine. This is otherwise represented as ARX, just like the alkyl halide, where R is an alkyl group, but here AR is a benzene group or phenyl group, what we call it. C6H5 is known as phenyl group. So this is aryl halide. In general formula of aryl halide or haloarine is that of ARX. AR stands for phenyl or C6H5 or other aromatic rings. For example, there are many types of example of this. You can say any or say chlorine, or in other words you can say CH3, bromine, etc., etc. Here we find the halogen atoms are directly linked to the benzene nucleus. So therefore these are called aromatic halide. Similarly, there are another type of aromatic halide where benzene ring is attached to side chain. When benzene ring is attached to side chain, it also has another type of CH2Cl. Now this is a aryl halide where aryl halide having X atom on side chain. Here halogen atom is present on the direct benzene ring, but here halogen atom present in side chain. Although benzene ring is there, but strictly speaking, these are not regarded as a aryl halide. They are similar to that of your alkyl halide. But here aryl halide literally we mean that when halogen atom is directly linked to the benzene ring. Now let us come to nomenclature of this compound. Just like that of other organic compounds, nomenclature of aryl halide, nomenclature of aryl halide, nomenclature of aryl halide. So here we find that aryl halide is named as per IUPAC name as well as also common name. Just like that of other organic compounds, there are two ways of naming popularly. One is called common ways of naming, another is called IUPAC ways of naming. In common ways of naming, common naming is simply aryl name of the aryl group, then add halogen, aryl halide, that is name of the aryl group, then just name of the halogen ending with IDE. But in case of common IUPAC name, IUPAC naming, this is haloarine. For example, you can say chlorine. A common name is benzyl chloride. Common name is chlorobenzene. IUPAC name is also chlorobenzene. Here both IUPAC and common name for this compound is same, identical. But in case of this compound CH3, say chlorine. So name of this compound is common name is your 2-chloro or orthochlorotoluene. But IUPAC name is 1-chloro 2-methyl benzene. These methyl group and halogen atoms, they are substituent. So name of the substituent comes as per alphabetical order. This is 1-chloro 2-methyl benzene. So common name is orthochlorotoluene. But in case of common naming, we use ortho, para, delta, ortho, para, meta, depending in case of multiple substituents on benzene ring. In common ways of naming, in in case of multiple substituents present on benzene ring, the name is given as ortho, para and meta isomers or meta compounds. For example, if we have, that is, you can say, that is, if in benzene one substituent is present here, say X, the other substituent, this substituent becomes ortho, this becomes meta, and this becomes para. Also here you can say parades, this is ortho. There are two ortho positions and two para positions. Sorry, this is meta dash. There are two ortho positions, two meta positions, one para positions. So in case of multiple substitution, one substitution is present means other carbon atoms becomes unequivalent. One is ortho, meta, para. Shortly we write is ortho, meta. For example, you can say, if you have chlorine, this is chlorine. This is ortho dichloro, or O dichlorobenzene. That means two halogen atoms are present on ortho to each other. So ortho dichloro. This is common. This is a common way of naming. But the IPAC naming is 1,2-dichlorobenzene. So in case of multiple substituents present on benzene ring, we write ortho, para or meta according to common ways naming, but in IPAC it is 1,2-dichloro. Similarly here it will be chlorine, say chlorine. This is meta dichloro, meta position dichlorobenzene, but it is 1,3-dichlorobenzene according to IPAC name. Similarly, if you have this position chlorine, then this will be para dichloro. O stands for ortho, M stands for meta, P stands for para dichlorobenzene, and according to IPAC it is 1,4-dichlorobenzene. So aryl halides having more than one halogen atoms on benzene ring are named as ortho, meta or para, depending on the position, whether it is 1,2 or 1,3 or 1,4. But according to IPAC name, it is 1,2, 1,3, 1,4 like that. So these are the nomenclature of halogen compounds. If you say aryl compounds, now let us come to methods of preparation. Aryl halide are prepared in a number of ways. One is by direct halogenation. When benzene is treated with halogen in presence of a halogen carrier like anhydrous aluminum chloride or anhydrous ferric chloride, then aryl halide is formed. That is, you can say, if we are treated with X2 in presence of anhydrous aluminum halide corresponding halide or anhydrous ferric halide, we get chlorine plus HCl. Here aluminum halide, sorry, this is X plus HX. Particular example if you take, for example, you say benzene treated with chlorine in presence of anhydrous aluminum chloride or anhydrous ferric chloride, we get plus HCl, chlorobenzene. This is a chlorobenzene. Here we see halogen atoms are directly substituting the benzene ring, that is replacing one hydrogen atom with the benzene ring. This is benzene. Similarly, if you treat it with bromine, in presence of anhydrous aluminum bromide or anhydrous anhydrous ferric bromide, the product form will be bromobenzene, HBr. This is bromobenzene. So in this way, directly we can substitute halogen atoms on benzene ring by this reaction. And another method of reaction is that of from diazonium salt. Second method of preparation is from diazonium chloride. Diazonium chloride is a compound like this. Diazonium chloride, we can say N double bond N Cl. Diazonium chloride is an resonance stabilized structure of two compounds, N triple bond N, this is plus, Cl minus. In short, we write it. In short, benzene diazonium chloride is written like this, is written as N2Cl, N2 plus, Cl minus, benzene diazonium chloride. When benzene diazonium chloride is heated with corresponding halo acids in presence of corresponding copper salt, if you are treating with benzene diazonium chloride with HCl in presence of cuprous chloride, then you can get chlorobenzene. And if you are treating it with benzene chloride with HBr in presence of cuprous bromide, you will get bromobenzene. So when benzene diazonium chloride is heated with HCl in presence of cuprous chloride, the product form will be chlorobenzene. N2Cl, N2 plus, Cl minus, plus if it is heated with HCl in presence of cuprous chloride, the product form will be chlorine plus N2 plus cupric chloride plus N2 plus Cl minus. So here you will find that this is chlorobenzene. If you treat it with N2 N2 plus Cl minus plus HBr in presence of cuprous bromide. The product form will be bromobenzene plus N2 plus Cl minus. So depending on which halogen atom you want to substitute, you can take that halo acids in presence of cuprous halide, corresponding cuprous halide. So this reaction is called, this reaction is called Sand-Meyer's reaction. Sand-Meyer's reaction. This is called Sand-Meyer's reaction. That means when you diazonium chloride is treated with HCl in presence of cuprous chloride, chlorobenzene is formed, and the reaction is called Sand-Meyer's reaction. And this reaction is also from diazonium. If you take in presence of cuprous halide, if you take metallic copper, then the reaction will be called Gattermann's reaction. The reaction is known as Gattermann's reaction. Third is from diazonium chloride, or is otherwise you can say third is by Gattermann's reaction. Gattermann's reaction. Gattermann reaction is a modification of Sand-Meyer reaction where the starting material is benzene diazonium chloride in presence of copper HCl in presence of metallic copper. Then you get corresponding halo acid, benzene. If you take say benzene diazonium chloride plus HCl in presence of copper powder. Mark the difference. Before the Sand-Meyer's reaction is copper chloride, but if you simply change cuprous chloride to metallic copper, the reaction is called Gattermann's reaction. Chlorine plus N2 Now here you find that Gattermann reaction, copper is taken in place of cuprous chloride. It is simply a modification of Sand-Meyer's reaction. Another method of preparation is that of only preparation of alkyl bromide, you can say. Preparation of aryl bromide only. This aryl bromide, this reaction is otherwise called Hansi-Dicker reaction. If you can recall, in the last class we have also discussed Hansi-Dicker reaction in the preparation of alkyl halide. Similarly, preparation of aryl halide is also used. What happens when silver salt of a carboxylic acid of benzene or aromatic carboxylic acid is treated with bromine, then the product is called halide, bromobenzene, and the reaction is called Hansi-Dicker reaction. That is, if you are taking COOH, this is silver benzoate, this is salt of benzoic acid, silver salt of benzoic acid. If it is treated with bromine in presence of neutral medium, carbon tetrachloride, the product is formed bromine. The product form is bromine plus carbon dioxide plus AgBr. So here you find that is the only method of preparation of bromobenzene, and this reaction is bromobenzene. This reaction is called Hansi-Dicker reaction. You can ask me why not chlorobenzene by this method? Because this reaction proceeds through free radical formation, and free radical is not formed by chlorine atoms because chlorine is a very reactive element. That is why chlorobenzene will not be formed by this method. So these are the methods of preparation of aryl halide. Now let us come to reactions of, or otherwise chemical properties. Chemical properties of aryl halide. Aryl halide. Chemical properties of aryl halide. Here, while discussing chemical properties of aryl halide, we have to discuss in two ways. That one is substitution of halogen atom on benzene ring, or the substitution of any other groups on benzene nucleus. There are two reactions. So while discussing these benzene rings, you must remember the aryl halide does not give any substitution reaction. The aryl halide does not give substitution, nucleophilic substitution, you can say, nucleophilic substitution reaction, that is SN reaction, easily. Contrary to that of unlike alkyl halide. That means we have seen in alkyl halide substitution reactions or nucleophilic substitutions are more easy, but in case of aryl halide, the substitution reaction is not easy. Or in other words, you can say, or in other words, the halogen atom in aryl halide is inert. That means the halogen atom is not easily replaced. That is otherwise called inertness of halogen. That is inertness of halogen in aryl halide. Inertness of halogen. Why halogen atoms of benzene ring is not replaced easily, unlike that of halogen atoms in alkyl halide, is due to some reasons, or due to the following reasons we can say. The alkyl halides, the halogen atoms are not easily replaced. The inertness, you can say, the inertness of halogen atom is explained by the following methods, by the following reasons. Number one is by resonance. As you know, we have discussed in your faster classes, the halobenzene shows resonance, where the lone pair of electron on halogen is withdrawn into the benzene ring. Thereby, a partial double bond is formed between the carbon and the halogen atoms. That is, you can say, suppose a X halogen atom is there. This lone pair of electron is present on halogen atoms. This lone pair of electron undergoes resonance. Due to resonance, you can say resonance occurs in halobenzene in this way. We get X plus minus here. This is one structure. Again, this negative charge polarizes in this direction to give you another resonating structure. Another resonating structure of this X plus. Again, this will polarize to give you another structure. Now, See, these are the resonating structures of halobenzene, and you observe that due to resonance, we are now having a partial double bond between this carbon atom and this halogen atom, this carbon halogen. In all these resonating structures, we see a partial double bond is developed between halogen and carbon, thereby the bond energy of this bond it becomes higher. As you know that the bond energy of triple bond is greater than that of double bond is greater than that of single bond. So where double bond is there, higher amount of energy is required to replace this halogen atom. This is one of the reasons that why the halogen atom is not easily replaced by any nucleophile in case of aryl halide. Again, another point is you can say by hybridization. You can also explain this on the basis of hybridization of carbon atom attached to X. If you consider the alkyl halide X, this alkyl halide and aryl halide. Here the carbon atom is saturated carbonate is sp3 hybridized. Here the carbon atom is sp2 hybridized. As you know, sp3 hybrid carbon atom are bond length is greater or elongated, and then sp2 carbon atom is shorter in bond length. Therefore, the carbon halogen bond in benzene ring is shorter than that of carbon halogen bond in alkyl halide. That is why higher energy is required to break this carbon halogen bond than that of your carbon halogen bond in alkyl halide. It has been observed that the bond length of carbon halogen in chlorobenzene is that of 1.69. Here this bond length is 1.69 angstrom, but here the bond length is 1.71 angstrom. So now we see that bond length here is shorter than that of your alkyl halide. Therefore, higher energy is required to break this than that of alkyl halide. Hence, the halogen atom is inert, is not easily replaced by any other nucleophile. Third point is that of by repulsion of electron cloud of benzene ring. We know that benzene ring is rich in electron because you know benzene has 3 pi bonds, and all these pi bonds are delocalized over the benzene ring, and that benzene ring is rich on electron cloud or electron density. Hence, when a nucleophile approaches the benzene ring, then it repels the incoming nucleophile. It does not allow to reach to the carbon atom to which the halogen atom is attached. Therefore, the benzene ring, the halogen atom is not easily replaced by any nucleophile. Hence, the benzene ring, the halobenzene is not, you can say, reactive, or you can say inert to any of the nucleophiles. That is why it is sometimes asked in the examination that why a methyl chloride is treated with silver nitrate solution gives a white precipitate, whereas chlorobenzene when treated with the same silver nitrate solution, no reaction occurs. That is when CH3 chlorine plus silver nitrate, it gives you a white precipitate of CH3 NO3 plus HgCl. This is your white precipitate. But the same reaction in case of chlorobenzene plus HgNO3, no reaction, or you can say no white precipitate. It is because of this carbon halogen stronger bond or inertness of this halogen. So this explains that halogen atom in benzene ring is inert to any of the nucleophiles, whereas that halogen atom present in alkyl halide is very reactive. Now, although this reaction is not easily, however, you can say the halogen, although the halogen atoms of benzene ring are inert, yet under drastic condition, the halogen atom can be replaced by other nucleophiles. For example, you can say in drastic conditions means strong nucleophile, higher concentration of reagent and high temperature and high pressure. So these are called drastic conditions. So under drastic condition, normally the halogen atom is not easily replaceable, but under drastic condition, the halogen atom is replaced by the nucleophile. Under drastic condition, the halogen atom of aryl halide can be replaced by a nucleophile. For example, when chlorobenzene is heated with sodium hydroxide at high pressure and high temperature, we get phenyl. That means the halogen atom is replaced by the OH groups. That means if you take chlorobenzene plus sodium hydroxide at high pressure, you can say high pressure and high temperature, aqueous, high pressure, about 400 degree Celsius, the product form will be ONA, which will be acidified to give you OH. Now you see, the OH group here is nucleophile. That nucleophile is replacing this halogen atom under high condition. Similarly, you can replace also, but ordinarily it is not replaceable, but under drastic condition you can replace this with other nucleophiles, like you can say potassium cyanide. Here potassium cyanide is treated with in presence of cuprous cyanide and high temperature, high pressure and high temperature, about 200 degree Celsius. The product form will be Cn. Here we find that cyanide ion is now replacing the halogen atoms plus cuprous chloride plus water. So you will find that under drastic condition there can be it is plus Cl minus, you can say. So under drastic condition you can replace this halogen atom by other nucleophiles, but ordinarily they are inert. On the other hand, you can say we can if a electron withdrawing group is present on this benzene ring, then the substitution becomes easier. When electron withdrawing groups are present on the benzene ring, the substitution becomes easier. For example, you can say in case of paranitochlorobenzene, nitro group is an electron chlorine, nitro group, and if you treat it but sodium hydroxide aqueous, then this will give you OH plus sodium chloride. Now here the OH group, OH minus, is replacing these halogen atoms in this condition easily because of presence of an electron withdrawing group. Therefore, presence of an electron withdrawing group in benzene nucleus, we can get substitutions on benzene ring, or you can replace the halogen atom. However, the halobenzenes or chlorobenzene, you can say, electrophilic substitution reactions, electrophilic substitution reactions, substitution reactions in aryl halide. In aryl halide, we find that, as you have discussed, that benzene ring is rich in electron, therefore an electrophile can easily be replacing the hydrogen atom on benzene ring. And electrophiles are positively charged species, they can easily attract the benzene ring. Therefore, in case of halobenzene or aryl halide, electrophilic substitution reaction on benzene ring occurs easily. For example, when chlorobenzene is treated with chlorine in presence of anhydrous aluminum chloride or anhydrous ferric chloride, we get orthochlorobenzene or parachlorobenzene. But the only difference is that here, or chlorine is here you can say here chlorine is orthopara directing. In your first year classes, you must have read the orientation in benzene ring. Chlorine atom is the electron donating group. All the electron donating groups are orthopara directed. That means they direct the second substituent into the ortho or para position. For that reason, when chlorobenzene is treated with chlorine in presence of anhydrous aluminum chloride, we get chlorobenzene plus chlorine in presence of anhydrous aluminum chloride. The product form will be chlorine plus chlorine. That means this is ortho dichlorobenzene. This is para dichlorobenzene. As I've told you that chlorine is a orthopara directing group, therefore two types of products will be ortho products and para. The halogen atoms will be replacing the hydrogen atom on ortho position and para position. Similarly, you carry out any other reactions, nitration, that nitration, the halogenation, nitration. As you know that benzene is nitrated in presence of concentrated sulfuric acid, concentrated nitric acid, concentrated sulfuric acid and concentrated nitric acid, and to give you nitrobenzene. But here in case of halogen chlorobenzene or aryl halide, the nitration is carried out in presence of concentrated sulfuric acid and concentrated nitric acid. The product form is orthochloride. Nitration here chlorine plus when it treated with concentrated HNO3 plus concentrated sulfuric acid, the product form will be similarly chlorine nitro plus chlorine nitro. So this is orthonitro chlorobenzene. This is para nitro chlorobenzene. So nitration, you will see that nitro group is substituting in the benzene ring. This is electrophilic substitution reaction. Third one is your sulfonation. Sulfonation, when chlorobenzene is treated with sulfuric acid, concentrated sulfuric acid, benzene sulfonic acid and parachlorobenzene sulfonic acid is formed. That is, when chlorobenzene is treated with concentrated sulfuric acid, the product form will be ortho plus SO3H. This is orthochlorobenzene, chlorobenzene, sulfonic sulfonic acid. This is parachlorobenzene, sulfonic acid, right? So these are the electrophilic substitution reaction where the electrophiles are substituting the benzene nucleus. Since halogen atom is orthopara directing, we are getting orthopara. Besides, just like that of alkyl halides, we have also reactions with alkyl halides, reaction with metals. Just like that of reaction with metals, Aryl halide reacts with metallic sodium in presence of dry ether. The product form will be alkyl halide, alkyl benzene, or aryl halide. Aryl halide, just like the Wurz reaction, you can say, when metallic chlorobenzene plus metallic sodium in presence of dry ether, we get two molecules of this. We get plus 2NaCl. Just like that of alkyl halide, here also we are getting this type of reaction is called Ullmann's reaction. Here we will get diphenyl. This is called diphenyl product. The reaction is called Ullmann's reaction. Similarly, when if you take a mixed, the reaction is called fatigue reaction. The reaction is called fatigue reaction. But if you are taking a mixture of alkyl halide and aryl halide in presence of metallic sodium, if you take a mixture of alkyl halide plus metallic sodium plus say CH3, CH2, chlorine in presence of ether, the product form will be CH3, CH2, CH3 plus sodium chloride, 2 molecules of sodium here, 2 atoms of sodium. So this reaction is called Wurz fatigue reaction. Just like that, Wurz fatigue reaction. This is called Wurz fatigue reaction. But if you take alkyl iodide in presence of heat in a sealed tube, the product form is called also diaryl, but that reaction is called Ullmann reactions. If you are taking aryl iodide and heating in metallic copper, you can say aryl iodide, heating it copper, metallic copper, 2 molecules of this, they condense to give you this is also a diphenyl, but in case cuprous iodide. But this reaction is called Ullmann's reaction. Ullmann's reaction. Mark the difference between fatigue reaction and Ullmann's reaction. Fatigue reaction is alkyl chloride in presence of metallic sodium in dry ether, but in case of Ullmann reaction, you are taking alkyl iodide in presence of copper powder, and the product form is also diphenyl. The reaction is called Ullmann reaction. Similarly, reaction with magnesium. Just like that alkyl halide, the aryl halide also react with magnesium. metallic reaction with metallic magnesium. Just like that of alkyl halide, aryl halide also reacts with metallic magnesium in presence of diether to give you a Grignard reagent type of compound, that is alkyl magnesium phenyl aryl magnesium compound, chlorine plus metallic magnesium in presence of diether. The product form will be magnesium chloride. This is phenyl magnesium chloride. This is just like that of, it's an organometallic compound, you can say organometallic compound, where we find that in place of alkyl groups we are having aryl groups. This is also a Grignard type of reaction. Grignard's reagent, just like that of RMGX, alkyl magnesium halide. This is also Grignard reagent. So these are all reactions of alkyl halide, aryl halide, and also we have in your syllabus, there are certain individual compounds like you can say gamaxine, DDT, and chloroform. We have other organometallic, haloalkanes or haloarenes, is that of your chloroform. First, all of you have heard about a chloroform which is used in anesthesia. General formula is CHCl3. This chloroform, which is prepared directly, you have read when alkane is treated with chlorine in presence of direct diffuse sunlight, the product form is chloroform. And that chloroform is used in anesthesia. But however, today this chloroform is not used as anesthesia because this is hazardous to human body. That is why it is now replaced by ether mixed with nitrous oxide as an anesthesia in your surgical experiments or surgery. Another reaction is called, another compound is called benzene gamaxine, you can say. Gamaxine is benzene BSC. This is shortly called benzene hexachloride. Benzene hexachloride, BSC, commonly known as gamaxine. The formula of this is all the hydrogen atoms of benzene are replaced by 6 halogen atoms. Formula of this benzene hexachloride is like this. So this benzene hexachloride, as you know, gamaxine is used as a you can say pesticides to control the pests, especially the ants. And nowadays this gamaxine is discontinued for use because it is not biodegradable. It is hazardous to human body because this gamaxine indirectly enters into our human body through various systems. Therefore, this benzene hexachloride or gamaxine has also been discontinued for use. Another reaction is called your DDT. This is dichloro diphenyl trichloro. This is dichloro diphenyl trichloroethane. So DDT is structurally you can write chlorine, CH here, C, Cl, Cl, Cl. This is the formula of DDT, dichloro diphenyl trichloroethane. So this compound is also used as a insecticides, just like this gamaxin to kill insects. But now, yes, again it has been discontinued because of its hazardous effect, because these compounds are not biodegradable. That is why they are not used nowadays. Another compound is that of your freons. You know, freons. Freons are compounds. This is also alkyl halides. These compounds are, you can say, used as an antifreeze. I mean, say, used as a coolant in our deep freezer or AC. We use this freons. This freon is dichloro-difluoromethane, CF2Cl2. And also there are so many freons, mixture of freons. This freon is called freon 1,2. Freon 1,2. This is difluoromethane. This is freon, and this compound is also alkyl halide, but this compound is nowadays its use has been discontinued because this freon compound is used to you can say ionize the ionosphere in atmosphere. So it destroys the ionosphere, in otherwise you can see creates a hole in ionosphere, as a result of which the sunlight, direct sunlight, or the hazardous effect, that is ultraviolet ray, enters into our atmosphere or into our earth, as a result of which caused lot of hazards. Thank you. Let us close this class today.